I had some cat matters to attend with. Like I mentioned yesterday, today is going to be a little bit on the short side just because I don't want to start the next tutorial until tomorrow, since the due date for the other free response isn't until tonight. So make sure that you finish up the Unit 5 free response tonight so that tomorrow when we go over the tutorial, you can follow along and participate. Today for the do now, I really just want to do a quick review of our demonstration that we did after energy but before momentum, just because it's a good demonstration to do conceptually, but at the time I said that we didn't have the time to do the math. So think back to when I put a tennis ball on top of a basketball, and just so that you know we have the correct parameters here, I'm going to drop both of these from a height of h. Where the mass of the tennis ball on top is going to be m sub t. The mass of the basketball below is going to be m sub b. And of course, the mass of the basketball is greater than the mass of the tennis ball. And who wants to give us a quick, sorry, let me let more people into the room. Who wants to give us a quick recap of like what happens with this particular demonstration? What was the occurrence?
Don't they stay together?
Say that again?
Don't they stay together?
As they fall, and I guess that is one part of this, they do fall together, and that's because all objects fall at the same rate due to gravity. Yeah, they both fall at the same rate due to gravity, so they stay together the whole time, but when they hit each other, what happens?
The tennis ball is like launched.
Yeah, the tennis ball is launched. Yeah, it goes way off, right? And the reason why that's strange is what do we normally observe when things bounce? What's the general rule that's applied? Every time it bounces back. What is loud? Can it bounce higher than it started from?
No.
No, it can't. And what conservation law is being enforced when you assume that?
Energy.
Energy conservation. So keep in mind that when it's dropped from some height, right, some mgh, that every single time a ball bounces back, it's going back to some new mgh. So let's say that I have a ball and I let it fall, and it's going to go ahead and it's going to bounce back to 3/4 of the original height, which is actually pretty wacky. Most balls only bounce back to about half the height they came from, unless, of course, you start by throwing them down. Because if you throw them down at the ground, what do they have? They have two types of energy that they're headed towards the ground with. What are the two?
Kinetic and potential.
They have kinetic and potential energy, which is why when you dribble a basketball, you have to give it a little push each time it comes back up, because if you just drop it, it's only going to bounce back up to about half of its height. But if we let this start off at some h, and then it bounces back to 3/4 h, we could take these two and divide them in order to get the efficiency. And this would be to say that the efficiency is equal to the energy out, because technically energy based on gravity is going to be mgh. So it would be h times mg divided by h times mg, energy out divided by energy in. All of these terms cancel, and this tells us that this ball is bouncing with approximately 75% efficiency. So every single time it bounces, it's going to bounce back up to 3/4 its height, 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 and as a result, it's going to decay away exponentially as time goes on. However, over here on the left, like Michael said, the tennis ball goes flying. Which is strange because if conservation of energy is true, it shouldn't do that. So is this breaking conservation of energy? Is that what's happening?
No.
Well, yeah, and that's actually a really good answer. If you're ever asked the question, hey, is this breaking conservation of energy? The answer is no, if it's in this universe, because there is no process in the entire universe which can defy the conservation of energy. It's probably the single most important singular rule in science, period. So no, it's not breaking conservation of energy. Something else is happening. Who wants to try and take a crack at what is occurring?
Isn't there like an exchange of energy?
Between what and what?
The tennis ball and the basketball.
That is exactly correct. And when two objects smash into each other, what do we call that?
A collision.
So this is to say that energy is transferred from the from the basketball to the tennis ball. And this is going to be some sort of elastic collision in an elastic collision. So when we did this, we just kind of talked about this vaguely, but we never sat down and actually did the math to prove this. So we're going to do that today, and then this will be the one thing we do today. So when we're done, y'all can head out. So we want to do all of the math for here to show that this tennis ball, if this is a perfectly elastic collision between these two, that it makes good sense that it can be bounced up higher than the original h. And so just like we did yesterday, where we outlined that second warm-up question in terms of events so that we could figure out what math do we need to do in each and every step. What math are we going to have to do here in each and every step? There's really a series of events that's going to occur. So what's the first event?
The drop.
The drop. So first off, we have to figure out what is going on with the free fall. So number one, we're going to do a free fall calculation in order to calculate how fast these two balls are moving based on the height that they fall from. And here we're going to make one pretty big assumption. We are going to assume the efficiency of the basketball. Now we need to do that because when the basketball hits the ground, the basketball is going to hit the ground and then it's going to come back up, right? So that when the collision occurs, the basketball is moving up, but the tennis ball is still moving down. And at that exact moment, that's why they have the collision that they do. So what do y'all think is a reasonable efficiency for a basketball? Like if you were to drop a basketball and just watch it bounce naturally, how high does it come back each time if it's properly inflated?
Probably more than halfway up.
Yeah, I'd say maybe a little bit more than half if it's a new basketball and it's properly inflated. Let's go ahead and assume 60% efficiency.
Okay.
So we are going to assume an efficiency equal to 0.6 for the bounce back of the basketball, so that after they fall to the ground, the next step is going to be, well, the basketball rebounds from the ground with 60% of its energy, and then it hits the tennis ball, which is still moving down, right?
Mhm.
So this is the moment of our collision. Basketball goes up, tennis ball is going down. And what type of interaction is that we would then need to calculate?
Elastic collision.
Number two, that is now an elastic collision. And after the elastic collision, think about the mathematics of momentum. What is that actually going to let us calculate? We do the math for an elastic collision and it's a bunch of equations, but in the end, what does it return back to us? You do all of the math of a collision, but what are you typically calculating when it comes to these momentum calculations? We're calculating final
Velocity.
We're calculating final velocities. So the whole point of that second step of doing the elastic collision math is we want, in the end, to return back the velocity of the tennis ball. So the goal here is to get the velocity final for the tennis ball. How fast is it going to come back? And then finally, that's going to give us our third calculation. What did we want to try and show? The tennis ball goes flying, and that's weird to us in terms of conservation of energy. Why? What height is this going to go to?
Like halfway or 60%.
No, that's the efficiency that the basketball is going to bounce back
The
with.
basketball.
What did the tennis ball do? How high did it fly back?
higher than it was from where it was released.
That's the one. It's going to come back to some new height. So the
Mhm.
goal here is to show that this tennis ball is going to bounce back and it's going to achieve some final height, which I'm going to call HF. And that is going to be a final height HF such that it is bigger than the original height, which is going to be finally, right, our calculation of final height. That is going to be a use of conservation of energy. So there's a lot of math to do here. This is a big problem. This is probably more complicated than any problem that they would ask you on the AP test. I just wanted to make sure that we still have this example down conceptually because it's a common question. Two balls drop together. When one of them impacts the ground and changes direction, they then have a head-on elastic collision, sending the ball on top flying. And what we're going to look at now is a general solution for this. Now, in my experience, we could solve it out all in variables, but I think one of the easiest ways that we can simplify the math is by expressing both of the masses of both of the balls in terms of one another. That is to say, to like give them as a ratio. So to start off, I'm going to look up the mass of a tennis ball, like the standard mass, should be about 58.5 grams. Then I'm also going to look up the mass of a basketball, like the standard mass for an NBA basketball, and it's about 0.625 kilograms. So that's 600 grams versus about 60 grams. So they have a mass ratio of about 10 to 1. Is that okay? Does that seem reasonable?
Mhm.
Yeah. So instead of working with an MB and an MT, I'm going to say that the mass of the tennis ball times 10, so 10 multiplied by the mass of the tennis ball is approximately equal to the mass of a basketball. Tennis ball is about 60 grams, basketball is about 600 grams. So using this, let's go ahead and begin. So number one, the easy part, free fall. How fast are they traveling when they hit the ground? To do this, we can use our simple which equation. Which equation are we going to use?
Kinematic.
We're going to use a kinematic equation because stuff falling is independent of mass. We
Mhm.
weren't given time, we weren't asked about time, and so we should go straight to the time independent equation. So both of these balls are going to fall the same height, h. So their final v squared is going to be equal to v naught squared plus 2a delta x. But we're talking about gravity, so what is our acceleration?
9.81.
9.81, which is g. And because we're not dribbling the ball, we're releasing them from rest. What is v naught?
0.
0. So this piece here, that's just 0. So the velocity that they hit the ground with is going to be equal to the square root of 2gh, where h is the height that they drop from. And both of them are falling the same height, so we don't have to do this calculation differently for the two. From here to here on the tennis ball, that distance is h. For the basketball, from here to here, that distance is h. So the tennis ball does start slightly higher, right? But the total distance fallen for both of them will be h by the time they have the collision. So now the second part, we need to do the math for the elastic collision, right? And so what is the velocity of the tennis ball? Velocity of the tennis ball. This is going to be equal to just this, right? And we're going to have to do some respect to signs here. So we said when I set this up here that I guess gravity is positive, right? Which means the downwards direction is positive. So at the moment of collision, the velocity of the tennis ball needs to be positive because it's moving downwards. So this is going to be equal to just the square root of 2gh. But the initial velocity of the basketball at the moment that they have the collision is going to have to be different necessarily. It's bouncing off the ground, so we're going to have to give it some amount of efficiency, right? We're assuming how much upwards velocity it's going to come back with. So I'm going to say that when the basketball returns, the velocity of the basketball, and our efficiency that we gave is 0.6, so we'll just use that. So it'll be times 0.6 root 2gh. But to make this good, I guess, we're going to have to do something else with it. What's missing from here?
The height.
No, the height is h. Which way is the basketball moving once it impacts the ground?
Back up.
It's moving upwards, but in the coordinate system I set up, g is positive, so that means downwards is positive. This is a positive velocity. The tennis ball is moving down. So what does this have to be?
Negative.
This has to be negative.
Wait, Mr.
So-
Robinson, why are you multiplying it like outside of the square?
Sorry?
Why are you multiplying it outside of the square?
Because if I multiplied it inside the square, that would give me a different answer. What this is saying is that when the basketball hits the ground, it's going to lose a little bit of energy to the ground. So it's going to bounce back with a slower speed. And here we're saying that when the basketball bounces back from the ground, it's not going to be traveling with the full root 2gh. It's only going to be bouncing back with 60% of that speed.
Okay.
Is that okay?
Mm-hmm.
Okay. So now for the big part. This is most of what this calculation is. We now need to do the math for an elastic collision. And doing the math for an elastic collision requires the use of two equations. What two equations hold when it comes to doing the math for an elastic collision?
Conservation of momentum and energy.
Conservation of momentum and conservation of energy. So now we're going to set up both of those statements and do calculations for both of those statements. So this is to say that mass of the tennis ball, velocity of the tennis ball, plus mass of the basketball, velocity of the basketball, is going to be equal to mass of the tennis ball, velocity of the tennis ball, plus mass of the basketball, velocity of the basketball, final. And this is not talking about the basketball colliding with the ground. This is talking about the tennis ball and the basketball colliding with each other. So these left-hand entries, those are going to be our initial values. The right-hand entries are going to be our final values. And of all of these things, what are we trying to solve for?
The velocity of the tennis ball.
We want the final velocity of the tennis ball here on the right side. The whole goal of this is to solve for that guy. So I'm going to give each one of these a 0 just to show that this is the velocity before the collision on the left-hand side. And now I can go ahead and plug in my terms, and then we can try and clean this up just so that the equation that we're playing with isn't so ugly. So on the left-hand side, that's going to be the mass of the tennis ball. And we'll be working on this in terms of tennis ball mass. So mass of the tennis ball multiplied by the velocity that it had as it fell. So in this case, it's going to be the square root of 2gh plus the mass of the basketball. But like I said, so that the math cleans up nicely, we looked up the masses, and the mass of one basketball is 10 times the mass of a tennis ball. So I'm going to go ahead and put that substitution in also. So it's going to be 10 times the mass of a tennis ball, right? So I'm just swapping basketball for 10 tennis balls, multiplied by its velocity, which is going to be equal to 0.6, I'm sorry, negative 0.6 root 2gh. Because after the basketball hits the ground, its initial velocity, the new initial velocity that we're using for the collision, is 60% of the speed that it hit the ground with, but then pointed upwards. And then this is going to be equal to the mass of the tennis ball, final velocity of the tennis ball, which is the variable that we're solving for, plus the mass of the basketball, which again, we want to put this all in terms of mt so that we can simplify, plus 10 times the mass of the tennis ball multiplied by the final velocity of the basketball. A fancy equation, but is this okay up until this point? Yeah? Are there any questions here? Okay. So now for the radical cleanup of this stuff. I'm going to divide everything by mass of the tennis ball. So the absolute value of the masses is actually irrelevant when it comes to collisions. All that survives is the ratio of the two masses. So it doesn't matter that the mass of the tennis ball is some number and that the mass of the basketball is some bigger number. What matters is the ratio. In this case, the ratio is 10 to 1. This is a weird thought, but that means that a 1 kilogram object colliding with a 10 kilogram object is going to have the exact same interaction, the same changes in velocity as a 1 million kilogram object colliding with a 10 million kilogram object. The only feature of that, which is determinative in terms of the final states, is the ratio of the masses. Anyway, so let's look at what that gives us on the left. This is going to be root 2gh plus negative 0.6 root 2gh. And this is going to be equal to, on the right-hand side, Vt plus 10 Vb. What can I do to the left to clean this up even more?
Cancel out 2gh.
Cancel out, factor out. I can factor out root 2gh. So this will be root 2gh multiplied by the quantity of what? What happens when I pull root 2gh out of root 2gh?
1.
1.
1 minus 0.6 is going to be equal to Vt plus 10 Vb, velocity tennis ball, velocity basketball. And now finally, this will give us our most simplified statement. 0.4 root 2gh is going to be equal to Vt plus 10 Vb. Now I have one equation with two variables, so how do I solve for these?
Set it equal to 0.
That will not allow me to solve for two variables. I have one equation with two variables. How do I solve for my variables?
Do you isolate for one and then use a different equation?
That's not that first part. Isolating them, that's optional, but that second part is mandatory. This is telling us we actually need a second equation. That's what the fundamental theorem of algebra is talking about, that the number of variables needs to be equal to the number of equations in order for a solution to exist. So if I have an equation with two variables, I either have made a mistake or there is another equation out there that relates these two that I need to then utilize. When it comes to these elastic collisions, this first one right here, this is only conservation of momentum. What's the other half of the coin when it comes to elastic collisions?
Conservation of energy.
Number 2, conservation of energy, which is, of course, 1/2 mass of the tennis ball, velocity of the tennis ball squared, plus 1/2 mass of the basketball, velocity of the basketball squared, which is going to be equal to 1/2 mass of the tennis ball, velocity of the tennis ball squared, plus 1/2 mass of the basketball, velocity of the basketball squared. Now I know that this is tedious, but if this comes up on the AP test, you get a lot of points just for writing down this statement, conservation of energy. And now that we've written it down, let's go ahead and start simplifying, feeding in our values, and seeing what happens. So first off, what's one thing that I can cancel out on both sides of this equation?
The 1/2 mv squared.
That would be to cancel out the entire equation.
Like
what is this? Huh?
Oh, never mind.
All the halves, right?
All of the halves can go away right off the bat. So I can multiply both sides of this equation by 2. And so these 1/2s are irrelevant. Now, don't get me wrong. The 1/2 does matter when you're doing kinetic energy work. So if you're setting potential energy equal to kinetic energy, the 1/2 is crucial in getting the correct answer. But for this statement, pure conservation of only kinetic energies, the half is irrelevant as a factor. Now what I'm going to do is I'm going to plug in our initial velocities, and then I'm going to square them, right? So both of these are going to get squared. And I'm also going to do that other thing where I replace the mass of the basketball with 10 times the mass of the tennis ball so that I can get rid of those mass factors. So mass of the tennis ball multiplied by the initial velocity of the tennis ball squared. So that'll be root 2gh quantity squared. And we'll see that something nifty happens there. Plus 10 times the mass of the tennis ball, because that's what the mass of the basketball is, then multiplied by the initial velocity of the basketball at the moment of collision, negative 0.6 root 2gh squared is going to be equal to mass of the tennis ball, final velocity of the tennis ball squared, plus 10 times the mass of the tennis ball, because again, this is just a way to get rid of the mass of the basketball by saying it's 10 times heavier than the tennis ball. Velocity of the basketball, then squared. And again, just like the other equation, the one up above, what do you notice I can divide out of everything everywhere right now?
The masses.
The mass of the tennis ball doesn't matter. So I can divide both sides by the mass of the tennis ball, and the absolute value is gone, but what will survive are these tens. So what matters is the ratio of these two masses. And also, this is nice. What is root 2gh squared?
2gh.
2gh, it gets rid of that square root. So now I'm going to go ahead and I'm going to clean this up as much as I can. So this is going to give me that 2gh. And then I got to square this. So this will be 0.6 squared, which 6 squared is 36. So this becomes 0.36. Squaring a negative makes it positive, so it'll become positive. So this will be plus 0.36 times 2gh is going to be equal to the velocity of the tennis ball squared plus 10 times the velocity of the basketball squared. And now again, on the left-hand side here, I'm going to factor out that 2gh. So this is going to be 2gh times 1 plus 0.36 is equal to vt squared plus 10vb squared. And I'll just clean this up on the left-hand side so it just becomes a number. So that's just going to be 1.036 times 2, 2.072. So the left-hand side here is 2.072 gh is equal to vt squared plus 10 vb squared. And so we're still not done. So the elastic collision procedure is I conserve momentum, which is this. I also conserve energy, which is this. I get two variables in two equations. What is the point?
Solve for the height.
That's what we're going to do in the end, but when we're just doing the elastic collision part, I get one conservation of energy statement, one conservation of momentum statement, and then what do I do with them?
Set them equal to each other.
We could set them equal to each other if both of these equations were linear. So if this was VT and this was VT, I could say solve both for VT, set them equal, and then that'll let us solve for their intersection. But is this equation linear?
Oh, no, it's not.
It's not. So think way back to pre-cal, we can set two linear equations equal, but what do we have to do with nonlinear equations?
It's like substitution or elimination.
The only method that can possibly work is substitution. So I'm going to go ahead and I'm going to carry both of these equations over to the next page, and then we'll substitute. We'll also talk a little bit about the math of substitution.
Mr. Robinson.
Yep.
Let's say like on the test, they would ask a question like this and we get something wrong in our math. Like, would they take a lot of points off?
No, and I don't believe this question could even be asked with the way they changed the standards. They would probably ask you about the concepts at the start, like
Okay.
how is it possible that the tennis ball goes higher than it started? And the only way to answer that would be to say, because of the conservation of momentum, you can show that energy is transferred from the basketball to the tennis ball. And so while energy is not conserved for the tennis ball alone, energy is conserved for the overall system. The tennis ball is getting up to that new height because it obtained energy from the basketball. But the extensiveness of this proof that we're doing, they would never ask for this. Even if they were, I would assert that 75, maybe even 80% of the points would be conferred to you before any of this was done, simply by the choice of this procedure of doing an elastic collision and setting up the momentum and the energy conservation. The rest of this work would be sprinkles on top in terms of your score. But by the time you had written this line down and this line down, you had already scored a 4.
Okay.
The difference between the rest of this algebra, which from here, this is just algebra, right? It's just being very careful. The rest of this is what the difference between a 4 and a 5.
Okay.
But yeah, just understanding enough to set this up is the 4. So here's my momentum equation, and then here's my energy equation. Wacky decimal. GH is equal to VT squared plus 10 VB squared. Now, if I want VT, what variable am I going to substitute across? Think back to algebra. If you're solving for x and y, how do you solve for x? What do you substitute across? If you want x, you substitute across
Y.
no y, and if you want y, you substitute across
X.
x. So whatever variable you are going to use to substitute across is not the variable you are going to end up with. So if you notice here, what I want is vt, I want vt, so I'm going to substitute across vb, I'm going to substitute across vb, because that's not what interests me here. Now, once you have vt, you could easily solve for vb, but just for your own knowledge, if you're doing substitution to get a variable, whatever variable you set equal between the equations, that variable will not appear in your answer. So here I'm going to solve for VB. So this is going to say VB is equal to 0.4 root 2GH minus VT, then divide everything by 10. Does that look good?
Mm-hmm.
Yeah, so I subtract this over, divide by 10, and now this is VB. And now the final step to solve for VT is to take this statement of VB and plug it in here and square it. So this is to say 2.072 GH is equal to VT squared plus 10 multiplied by the quantity of 0.4 root. And I hope y'all can see why we didn't do this as the intro to the section, because if I did this as the intro to the section, everybody would have ran screaming. 0.42 GH minus VT, all divided by 10 squared. So this is just me taking this redefinition for the final velocity of the basketball and plugging it into the conservation of energy equation. So this has come down in its form. So the left-hand side is the same, VT squared is the same, the 10 is 10. The only thing I'm doing is I'm saying VB squared is actually this squared. And now notice this equation has how many different variables in it? We have one equation, and how many variables are in this one equation?
One variable.
There's only one variable. It appears twice because this is a quadratic, but there's one variable, there's only VT, there's one equation, and so that means that this is doable, so let's go ahead and do it. So the first thing that I'm going to do is I'm going to square in here, but I'm going to do some clever math junk that I think you should look at before you guys are asked to do college level algebra next year. Now I could hit it with the brute force, or I could be smart. I'm going to be smart. This is going to be equal to VT squared plus 10 times, well, when I square a fraction, I'm going to square the numerator and the denominator independently, yeah? And so I'm going to say that this is the numerator squared, which I'm not going to touch yet. We'll have to touch it in a second, but not yet. Minus VT squared, all divided by 10 squared. Why would I square the numerator and the denominator independently in this case? Something cancels.
Trying to simplify with the 10.
Yeah, it simplifies with the 10. So this 10 cancels out with one of the 10s in the denominator, because 10 squared is 10 times 10. And now there's only one single 10 down here. Now I'm also going to multiply both sides of the equation by 10, because fractions are for suckers if you don't have to deal with them. And by multiplying the entire equation by 10, no more fractions. So I multiplied this guy here by 10. It just moves the decimal over. So that's 20.72 GH is equal to 10 VT squared plus whatever junk is in here squared, 0.4 root 2GH minus VT quantity squared. So that's how we go from that nasty stuff with a fraction in it to less nasty stuff without a fraction in it. Is this okay? Okay. And now squaring this. What do I get when I square this stuff on the left?
2GH just turns into regular 2GH. And then 0.4.
Let me ask it this way. What's A minus B squared?
Isn't it a squared minus ab minus b squared?
Say that one more time, Jack.
A squared minus ab minus b squared? Or I probably got the signs wrong somewhere.
So please notice that this is not a squared minus b squared. When you take this thing and you square it, you have to FOIL it with itself, which is going to produce 3 terms, a squared, and then minus ab, and then minus ab, which is minus 2ab, then plus b squared, because a negative times a negative will give us a positive. Remember forever that squaring a binomial requires some FOILing. Some funky stuff is going to happen. So when we take this term here and we square it, it's actually going to make 3 terms for us, not 2. So I'll square this guy out. First, we're going to take this homie up front, and he gets squared. So that'll be 0.4 squared. 4 squared is 16, so it becomes 0.16. And Rachel, you were correct. When this part gets squared, it just becomes 2gh. So this homie squared, our equivalent of a squared, is going to be 0.16 times 2gh. And then the middle part is going to be minus 2 times the product of these guys. So it's going to be minus 2 times 0.4 will give us 0.8 root 2gh bt. And then finally, this last part is going to get added and squared, so it'll be plus bt squared. Is that okay? That's just this squared. It produces these 3 terms. And then on the left-hand side, this is going to give us 10 vt squared. And on the left-hand side, we have 20.72 gh. And now, kind of final procedures. I'm going to clean this up a lot. So I'm actually going to clean this up to the point that I say 0 is equal to 11 vt squared plus, as clean as possible in one step, yeah? 11 vt squared minus 0.8 root 2gh vt. And then finally minus, notice this is in terms of GHs and this is in terms of GHs, and those are going to be our constants. So I'm going to say 2 times 0.16, 2 times 0.16. This is actually 0.32 GH. From that, I'm going to subtract 20.72. So negative 20.4. So it's going to be minus 20.4 GH. And now, big brain time. What equation is this? Who is that?
Wait, Mr. Rob.
Yeah.
Could you go up a little, please? Why is it still 10 v sub t squared? Because earlier I thought you canceled one of the 10s with the 10 in the denominator, and then you multiplied it to the left with 2.072.
Yeah, so right here, this 10 cancels with this 10, which leaves 1 10 in the denominator. The other thing that I did in this line was I multiplied the whole equation by 10 to get rid of this 10 entirely, but that tags a 10 on here, and that also tags a 10 on here, which is why we go from 2 to 20.
Oh, all right. Okay.
Does that answer your question?
Yeah.
It's a great question. Now, like I said, we end up here after all of that work, so much algebra, right?
Yeah.
What equation is this? Who is that? How do we solve an equation of this form?
Factoring.
If you were a genius and you could find a way to factor this, great, but I'm asking what kind of equation is it? What equations do you solve by factoring?
Quadratic.
This is a quadratic equation. This is exactly the same as the equation a x squared plus b x plus c is equal to 0. And how do we solve quadratic equations?
Oh, you can use the quadratic
formula.
You use the quadratic equation or you complete the square. Since there are variables buried in here, really the only thing we can do is the quadratic equation. So x is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Here's what I would like y'all to do tonight for the homework, is to just finish up this proof. It shouldn't be that long, but please do take and calculate VT is equal to this. And you know, what was the whole point of this? We wanted to show that when the tennis ball bounces back, what will happen?
It'll go higher than where it released from.
After you have a statement of VT, show that the tennis ball bounces back higher. This is to say that when it bounces back, it's going to have kinetic energy, 1/2 mv squared. And when it bounces all the way back up, that's going to bounce up and become gravitational potential energy, which is going to be mgh. So please show that the final height, h sub t, is greater than h. You will be able to show it by using this equivalence. It'll be something about how the variables are related on the inside. Take a little bit of time to do this tonight. You'll also find that the inside part of the quadratic equation here cleans up pretty nice. Take this a, 11, this b, and keep in mind that b is negative. Plug it in both here where you see b, and notice that this c is also negative. Plug it in here and simplify this down, and you should be able to show that the velocity of the tennis ball will cause it to bounce up higher. And on top of that, the units will also check. Even though you're taking these complex terms and plugging them into this form, this will still give you back units of meters per second because you're solving for a velocity. This question is a lot like the questions that the AP test used to carry before they did the realignment, before they changed it from AP Physics 1 to AP Physics, I'm sorry, from AP Physics B to AP Physics 1 and 2. I just think that this is a good exercise, especially to do before you go to college, because this is what your freshman physics courses will look like. This is the type of thing they will expect you to do and manipulate.
Okay.
So like I said, I took you guys 90% of the way. Do the last 10%. I'm going to ask you guys to do this, and then this will be due tomorrow right before class. I just want you to upload your best attempt at it. I'll put it on Classroom and put a due date and stuff. And then we'll go over this tomorrow as the warm-up, and then we'll get into our tutorial for the Unit 5 free response. You all have a very nice day, and I'll see you tomorrow on Friday.
See you.
See.
Mm-hmm.